Welcome to our most recent lecture on recursion. Recursion is one of the central ideas of computer science, especially when it comes to formulating more complex algorithms. Why is it so important to us in this class where we've been studying algorithmic analysis and algorithms in general? Because divide and conquer solutions are oftentimes some of the best solutions to problems that have more than one solution, especially in terms of run and memory efficiency. Just to review, let's go over what iteration is. Iteration is loops, like for, to, and while, as I'm sure you're all familiar with. But the algorithmic complexity of these loops is an important component. So, for two lists size n and m, quickly remind me, what is the efficiency of finding all of the unique matches between them? A lot of you are saying O of n times m times k, that is the average efficiency for k common matches. What's the worst case efficiency? O of n squared, that's right, yeah. Where n in this case is the same size as m, that would be the worst case efficiency. And you can see this from counting the number of nested loops that you have to go through. Recursion is going to be a much different beast, but it's also going to be mathematically and algorithmically a little bit more elegant. This elegance you can see in kind of our natural interpretation of what people might call meta or recursive occurrences in real life. So, in order to understand recursion, you must first understand recursion. Fractals that exist in many parts of nature, including astronomy of flowers, games that we play, like 2048. Google, of course, has its own little computer science jokes on recursion. And things as diverse as little nursery tales and Matryoshka dolls, or Russian nesting dolls. But what is a good illustration of recursion as far as we are concerned in this class? Well, let's look at the factorial. What is the factorial? Factorial of a number is that number times all of the numbers below it down to 1, for all kind of positive integers, as it were, natural numbers. So you can think of this in two ways. You can think of it either as 7 times 6 times 5 times 4 times 3 times 2 times 1 for factorial 7. Or you could think of it as 7 times 6 factorial, which can then be reduced into 7 times 6 times 5 factorial, and so on and so forth. This is a slightly more natural way maybe to think about what's going on here. But this is an example of primitive recursion. This is algorithm, as many that I'm sure you'd be familiar with at this point, that doesn't require recursion or doesn't even really benefit from it in any way, except for that the code you might be designing is maybe a little bit more language agnostic or more elegant to read. So exactly why do we care about recursion? Well, we don't. No, I'm just kidding. But actually, there are a lot of instances in which recursion isn't that important. There is rarely a big O efficiency advantage to using just recursion, especially in simple situations like the one we just looked at, where recursion can be easily subbed out for iteration or looping. There's also a big advantage for looping, or not big, but noticeable, in modern languages. This is partially because the object-oriented nature of these languages creates functions in somewhat of a inefficient way on the call stack to ensure that they can be passed around properly and work with each other properly. They it can be more intuitive as well to do something iteratively. Some of you may think that the factorial method was more intuitive to do iteratively, kind of going down the line of a series, a sequence, but some of you may have thought that the iterative method was more intuitive. Iteration, of course, is also way simpler to debug in a language like Python. This is a blessing and a curse of recursion. In recursion, you have nice, only local variables that you're dealing with and very little mutation, but you can't see all the values of what's going on as a result. In iteration, you obviously can't. Everything is scoped. And especially in a language that's interpreted like Python, this is important. And almost all examples of recursion, as I kind of mentioned before, can be written as iteration, especially the simple ones. And memory constraints are a huge issue with recursion. So in iteration, you're pretty much just keeping as much memory as you specifically assigned. Whereas in recursion, you can end up with some serious memory constraint problems on the call stack and even stack overflow, which is where the site gets its name. But really, why are we doing this? The reality is that recursion is really elegant. It can be much more intuitive for certain things, especially if some of you are previously familiar with recursion, the Fibonacci sequence, which is defined in terms of previously calculated iterations of the Fibonacci sequence. It can be, in this way, a direct relationship between mathematical functions and the code that codes them. It can have less code, like we saw in the factorial example, and we'll see in the future. And this way it can be more elegant. Some languages, notably functional languages, do not have iteration always. Haskell, for example, pretty much requires that you use recursion for looping through things. Then it also has small advantages in terms of kind of good practices. So there isn't as much variable change, so you can be confident what a variable is at any given time, because if you're treating functions as recursive and algorithms as recursive, then you're inherently believing that the variables at each scope are not mutable, because if you want to mutate them, you usually just call another function. And as opposed to in a loop where they're just changed for the sake of the algorithm, like you have to do arithmetic that way. Complex algorithms are often simplified when reasoned about recursively, or using kind of some combination of recursion and iteration. Quicksort and merge sort are two examples of this. Backtracing or backtracking, that's kind of a common way to solve maze problems or anything else that has a tree-like structure. And most dynamic programming problems, which is something we'll get to in our next lecture, are solved using some level of recursion, if not entirely with recursion. And then sometimes you don't have a choice. The Ackermann function, for example, is a total recursive function that does not have an iterative counterpart. Most of these types of functions don't really have much basis in kind of functional reality. We don't use them that much for actual stuff, but it is important to take note of. And then lastly, the stack versus the heap. The stack is inherently, in a computer, a easier thing to write to. Whether the language you're using at any given time, based on its paradigm, allows it to actually remain quicker, is a completely separate issue, as I mentioned, the kind of cons for recursion, but it is, in fact, a faster place to write to. So, to look at recursion, we're going to look at a small problem called the Tower of Hanoi. So the Tower of Hanoi is something that you might have been familiarized with as a children's toy. It's a puzzle, basically. The idea is that you have n disks on a rod, and there's 3 rods, and you may only move one disk at a time. The disks must be placed on the ground or a disk larger than itself. And the objective is to move the entire pyramid of disks from the leftmost rod to the rightmost rod, or in the case that you're starting on the rightmost rod to the leftmost rod, using the center rod only as an auxiliary. So let's define our function as such. Tower of Hanoi of the size of our stack, n, we're trying to start at a certain rod, move to a different rod, and then use our auxiliary rod as a helper to move these disks around. So for a stack of 4, we would see Tower of Hanoi, 4, and then if the rods are A through C, 4, moving it from A to C using B. Any questions? Okay, great. So moving forward, this is the setup of our problem. So we can imagine that, as I kind of alluded to with recursion being fundamental to divide and conquer algorithms, we're going to think of this stack as being divisible into similar, smaller towers of Hanoi. So we can think about the top 3 disks as being their own tower, and we can imagine that if we want to move the entire tower to C, kind of the basic criteria we need is to get the bottom disk, which can't go on anything except for the ground, over to rod C. So we know we need to break it down into having a tower of 3, and that's going to move somewhere besides C, so we'll put it on B. So we're going to move a tower of 3 from A to B. We're going to move the red disk to C, and then somehow we're going to get the rest of that stack over to C. And you'll see from our breakdown here how we're going to do that. So, kind of following in the steps of this idea, we're now going to break down each of these tower of 3 Hanoi towers down to their constituents. So, we're going to, knowing that we have this tower of 3 that is currently on A, and we want to get it to B for the previous step, we need to move the blue disk, the largest disk, not counting the red one, over to B. So, starting at A with a tower of 2, that's the 2 that are on top of the blue disk, we're going to move that stack of 2 over to C, using B as the auxiliary, and then when that's done, move the blue disk to B, and then move them back on top of the blue disk. That would give us the tower of 3 on B that we were talking about in the previous step. But we have to break that down again, because we can't move 2 disks at a time. We'll only move 1. So, breaking down this stack of 2, we have Tower of Hanoi of 1 disk, the purple disk, moving it from A to B, because remember, we want to get the green disk to C, so we can get the blue disk to B, so we can get the red disk to C. That's the intermediate step that we're using kind of as our goal to construct all this. And then, after moving the green disk to C, we can move the purple back on top of it. And actually, we're kind of ready to start moving things, because a Tower of Hanoi function applied to only 1 disk is just a move. So, applying that, we're going to move Tower of Hanoi, we're going to execute Tower of Hanoi 1 ABC by taking the purple disk and putting it on B. From there, we can put the green disk on C, and then move the purple disk back over on top of the green disk. Easy. Now what? Okay, so we can move the blue disk to rod B, but then we have another Tower of Hanoi, 2CAB. So, we're going to treat this again as its own tower, and I'm going to take a minute here, and I want everyone to discuss with the person sitting next to them what they think the function line, what needs to happen here, based on what you've seen before, so that we can get those 2 disks to where they need to be. Okay, so if you said that this Tower of Hanoi of 2CBA, aka moving the green and purple disk over to B from where they currently are on C, was broken down as moving the purple to A, moving green to B, and the purple on top, back on top of B, you were correct. And that's how we get it to the middle. And now, we're back with our original intermediate goal, getting the substack to B, so we can get the biggest disk that can't sit on top of anything else over to C. So, what do we do next? We have another tower of 3. We need to decompose it so that we can get it all the way over to C. Now take about 2 minutes here, discuss with the person next to you. See if you can really write down actually the procedure of what's going to happen to get all those disks over. Alright, so I think that was about 2 minutes. So the answer is breaking down into another problem, Tower of Hanoi, 2BAC. That is to say, taking this tower of 3, taking the top 2, and saying that we need to move that top 2 over to A before we can move B to C, which itself is broken down into moving purple from where it is B onto C, moving green to A, and then putting purple back on top of it on A, so you can move B to C, then followed by breaking down this tower of 2 again, which is now on A, so that you move purple to B, green from A to C, and then purple, lastly, from B to C. We have our tower. We did it! So, all that work, all that complexity, these 5 lines of code. That is part of the impressiveness of recursion. You take this very complex idea, and then you can squeeze it into maybe kind of its most mathematically representative solution, and you can do it in code, which is really nice. You have a representation of exactly what needs to go on procedurally and to actually execute this, and it scales. All of this works for a tower of size n. But let's bring this full circle. How do we measure the efficiency of a tower of Hanoi algorithm? How do you measure the efficiency of a recursive algorithm? Using the towers of Hanoi idea with n disks, what we're going to do is start off by taking the original function, which was towers of Hanoi of n number of disks, and then we can kind of skip the rods for now because the number of operations is pretty much only dependent on n. We're keeping the number of rods fixed, is equal to the number of operations of a tower 1 smaller plus a move operation plus the number of operations for a tower 1 smaller. That's exactly what we're doing. So we have a yet unknown function of operations, m of n, equal to 2 times m of n minus 1 plus 1. And we know that m of 1, kind of like having just a purple disk, is 1. It's just a move operation. So what we're going to try and do with this equation for m of n, this recursive equation for m of n, is we're going to try to change it up and insert things here and there so that we can completely eliminate m from the right side of our equation and have m of n only in terms of n. This will be the first step to giving us our efficiency. We're going to do this using back substitution. Pretty much a self-explanatory name. We're going to substitute m and variance of n back into the equations we find. So we have m of n is equal to 2 times m of n minus 1 plus 1. But now we just insert m of n minus 2 in for m minus 1. So we get the following equation. And why don't we repeat it? Why don't we substitute m of n minus 3 for m of n minus 2? You might be, if you're looking carefully, starting to see a trend here of how this is changing. Especially if you remember your Calc 2, you'll come up with the following solution for any iteration I. When I say iteration, I mean not actually we are iterating, but any kind of n minus value, which is this. Now, we can say, okay, with this general equation, for any substitution for I, where I can be anything from n to n minus 1, all the way down to just 1, what do we want to substitute I for, such that the m term is m of 1? aka how can we cancel out the n that's inside m of n? Well, we substitute n minus 1. So substituting n minus 1 in for I, we get the following. 2 to the n minus 1 times m of n minus 1, which is 1, plus 2 to the n minus 1 minus 1 is equal to 2 to the n minus 1. So what's our efficiency? Exponential. O2 to the n. You might have started to actually get some intuition as to that by just watching us go through it in the beginning. I don't know, did anyone get that? But so, what does this mean? Does this mean that recursion is awful, has awful runtimes, we shouldn't use it ever? No. The interesting thing about recursion is how, especially with divide and conquer algorithms, it fits into dynamic programming. We're going to use dynamic programming to enhance recursion and to make these algorithms that run slow in both iteration and recursion to make them actually run fast. Sometimes, like in the case of the Fibonacci sequence, in linear time. And now, your memes, or should I say, algorithm memes.